nanophotonics. And nanophotonics means very small with light. Now this is a bit strange topic actually, because light has a certain wavelength, which is not nano, it's much larger, it's about 1000 nanometers, and we still want to work nano. So this is a bit paradox actually, and light doesn't allow to do that. So if you're working with lenses and normal optics, that just doesn't do it, so you have to work with something else. And so what we do is we find methods, and this conference where we had today is a Plasmonics conference, and this stands for small particles where there's electronic oscillations and still the light frequency, and this allows you to go really small. And that's the whole idea here. And so we're trying to understand this, we're trying to prepare it, to fabricate it, and in the end get it to work. And me personally, I like a lot to look at molecules, just molecules one by one by one. These are even smaller, and so to get the light down to a molecule, this Plasmonics is really ideal. So we're making very small particles. These small particles, we make them resonant so that the right colors are enhanced by these particles. We put them very close to the molecule. That way we can, on a nanometer scale, make things interact. And we can look at these molecules almost as small as they are. Almost, just not, but we're getting there, we're getting there. So that's good. That's good for microscopy, or nowadays they call that nanoscopy. Yeah? What I like is to see then what the molecule does. So I like to see how it moves, what the dynamics is, and this is at the femtosecond, picosecond time scale. So what I do, I combine this very small optics with very fast optics. This is my field of research. Why would you do all that, you might wonder? Well, for the fun of it, for the Guinness Book, for good papers, publications, but also because many processes in nature actually require that you look at the level of one molecule and see how things interact. What I particularly like is biological systems, photosynthetic systems. They have energy transfer. And this energy transfer of these systems, you know what happens there? It's at the nanometer scale and it's ultra fast. Yeah? And so I'd like to combine it. And so we'd like to see how that light jumps from one to the next, to the next, to the next molecule. And we're getting there. Nature is very clever. It harvests the sunlight, and it does that in the so-called photosynthetic complexes in a very fast but also very efficient way. More than 90% efficiency, which is a lot better than we can do personally in any artificial system we make. So what we like to see is, how does this molecular process jump on from one to the next, to the next, to the next? How does it do it so efficiently? How does it beat anything we managed to make ourselves so far? And perhaps we can learn lessons out of that. Yeah? That's what we're trying to get.